So first thing is, any questions from sections after 3.4? Or anything left over that we didn't get to earlier?
Two off the weather side.
Sure. From 3.5?
Yes.
All right. Oh, yeah, all right. So this one gives this. And it wants to find dx dy. Now, real quick, remind me, y prime is also represented by what notation?
D over dx.
Yeah, dy dx. Cool. And this means this notation is actually a little better than the prime notation, yeah.
I'm a little confused on like the d over dx, dx over dy, and dy over dx, and then du over the dx.
That's what I'm getting into right now.
All right.
You ready? So remember what I said when we first looked at this notation. Why is this better than y prime? Because this is a little more specific. This says take the derivative of some function with respect to x. So I know that all my x's are my true variables in this case, right? You guys with me? And my y's would be functions of x. So they're the ones I would need the y prime. The dy dx is attached onto them.
So if they write that without the y on the top, does that imply the same as dy?
If they write what now?
Just
A lot of times they'll write d over dx. They
Yeah,
won't
because
write
again, f prime of x is df dx. So what's like the prime thing by itself? D dx of something.
Okay.
It's like an empty square root sign. So that's why I really don't write that very often, because it is missing its input. So by itself, it doesn't make a lot of sense because I'm not doing anything to something yet.
Weather
So-
sign, unless they're doing like chains or big things, they write a d over dx.
I like it. That's cool. It's a good way to be. So if I did dy dx, that means I did, what did I do to this side? Yeah, y prime. So I did d by dx. I took the derivative of this with respect to x. So I better do the same damn thing to the other side, right? I'm way overanalyzing this thing. But just to make a point related to what you're saying. So this side I have to do d by dx to x. But what's dx over dx?
1.
So of course, if y equals x, y prime is 1, right? You with me? But do you see why? Because I'm taking the derivative with respect to x. So x derivative would be 1. But here, what do they ask me to do? Take the derivative with respect to y. Which means everything's turned around now. All my stuff. So if I did this, one way you could do this is, what do I have to use here? Product rule. So it would be, you could actually, if you wanted, you could write dy dy. Is that cool? Especially when you're doing something weird like this, because your primes now, the reason prime notation is, we use it a lot at first because we only have one variable normally, x. So prime means derivative with respect to x. But in general, you have to be more specific. What are you treating as your variable? Which one is the function of the other variable? So here, if I did this guy, I'd have to do a product rule. Plus y d secant x dy.
Where does secant come from?
It's what I'm taking the derivative of. Right? That's the problem you asked me to do. Okay. So I just did product rule. Did product rule. Okay. On the other side, same thing. Do product rule. D5x dx. Oh, sorry. dy. Tangent y. Plus, leave 5x alone. Do the derivative with respect to y of tangent y. Yes, sir.
I don't know if you explained this when I was on, but why did you use the dy, the dy's and the d? Why is there d's now?
There has always been. It's just we have a choice between notation. We have a choice in notation.
Okay.
So So prime is good when you're first learning all the little rules, because you don't want to have a lot of stuff to worry about. Now we're getting to the point where our variable might not always be x. And in fact, today we're going to get into one where our variable will be t for time. So we normally, in the physical sciences, we're worried about how things change over time. So we're going to be doing a lot of dy, dt, dx, dt, dv, dt for volume. How does the volume change in time? Right, the creature is growing exponentially. Oh, shit. So right there, instead of doing primes, which were sort of geared towards meaning derivative with respect to x, I'm not going to use that here for that very reason. They want me to take derivative with respect to y. So I want to be a little more clear to myself what the hell's going on. So what's the derivative of y with respect to y? 1. So then you're just left with secant x. Now what's the derivative of secant x?
It's
Tangent x.
tangent x times secant.
So tangent x, secant x. And then doesn't the inside get a term? And what would that be? What am I taking the respect to? dy. And what am I taking it of? There you go. So that's sort of like putting a y prime for the chain rule. Now it would be an x prime, but our brains are really geared towards that being 1. Here it's not 1. I don't know what the hell it is. And we all know to a point, if I have y equals 2x minus 1, that's the same thing as x equals y plus 1 over 2. It's y as a function of x, or x is a function of y. Who cares? Okay, how are we doing so far? Decent?
I didn't really get the math part of it.
Yeah,
So when you normally, if we did secant y derivative, we're doing implicit differentiation, what would you have to do?
You'd have to multiply by y prime.
It'd be secant y tangent y, and then you're right, times y prime, which is really dy dx. So I'm doing the same thing, except now x and y have just switched their meaning. They're looking at it like this now, like x is a function of y. So x prime is not 1 anymore. So we have to start letting go of our y and x is exactly this and exactly, because it's not. We don't.
You're saying x prime is dx dy now?
Second.
Is that what you're saying x prime is?
Yeah, this would, yeah, exactly.
Oh, all right. That makes
Because we're taking the derivative with respect to y. So the prime notation is really good when you're first learning the rules and you don't want to bring a lot of excess stuff in the way. You just want to get the rules down. Then you need to start to transition to a broader idea of, well, it's not always going to be x as my variable. Maybe it's turned around. And that's where the Leibniz notation is a little more geared towards that. It's a little more specific about what are you taking the derivative with respect to. Let's see, where did I leave off? Okay, so that's here. Equals, what's the derivative of 5x?
5x dy.
Yeah, 5 dx dy. Because I don't know, x is a function of y. I don't know what its derivative is. So it's like putting y prime, but now it's x prime. Plus 5x, what's the derivative of tangent? Secant squared. Do I need a y prime or something? No, because dy is 1. Just like dx is 1. So you guys love this, I know. It's not your fault. You've been geared throughout all of algebra to think of things like this. But y and x are just dummy variables. Why are they y and x? I don't know. But it could have been the other way around. Or it could be v and t, volume and time. So you got to let go of the specific variables meaning things and just go with what the situation says is going on.
Is there a reason that they even bothered doing the y prime 1? Because I mean, it gets our heads so far into that. Now we're learning. Honestly, I'm learning this all new right now.
No, from the very beginning. From the very beginning, I told you this. And I also told you that Leibniz notation, why does this exist? For when you have problems where you have other variables, or in this case where the variables mean different things. So you want to be more specific in those cases.
Okay.
I didn't think that meant anything. I thought the common thing was more important.
Common thing. These mean the same thing. Yeah. It's just that this is a lot more specific. Okay. So you see, I didn't want to go through this while I was trying to teach you product rule and chain rule. Kind of way. I want you to understand those rules entirely, and then you're going to suffer a little bit to get used to this, instead of suffering throughout those rules with this while you're trying to get this up.
Question mark. What's this like called? What's this like? You know, when I was just learning implicit
Style and notation.
Yeah, so I can like YouTube.
This is still implicit.
Oh, it is.
It is.
Okay.
You can search for implicit differentiation with respect to y.
Okay.
It might have something specific about that.
So pretty much we should almost be done writing y prime.
No, it definitely still has its purpose. It's just, in fact, I've said this a few times when we were doing the prime thing. I said we have to be careful that we understand prime in this case means respect to x. It's just that every problem so far has been like that. And again, I could either have put the suffering and spread it out a little more earlier, or I could have saved it till right now. And I just chose to save it till right now. At some point there was going to be some suffering, some getting over this. And I wanted you to have some idea of calculus first before I started throwing this at you too. And you kind of gave up, all calculus is bullshit. No, you got calculus, you understand calculus now. You know what it's all about. Now let's talk about this weird shit. That was how I designed the class. I could go either way. And it almost doesn't matter. But I got to make a decision, yeah.
What is it? What about when it has like...
Well, let's finish this one up real quick.
Okay.
And then I want to show you a cool thing you can do. What's the next idea in any implicit differentiation? I'm trying to find what?
Y prime.
X
By
prime.
itself.
In this case, x prime, right? dx dy.
Oh.
So you could look at this. This is sort of the same thing as x prime, but the prime notation is just not specific, right? Before that would have been 1. Here, I don't know what the hell it is. So anything that has a dx dy in it, I want to get that stuff together.
What causes it for you not to know what it is?
Because nobody told me.
Oh, okay.
That's why it's called implicit. Implicit is like when the tiger drags the thing behind the bush and you don't get to see it chow down. It's implied that the thing it dragged is dying. Right?
Yeah.
Okay, nobody liked my National Geographic implicit death.
The other ones are horrible.
Who knows? Maybe the rabbit just killed him. We don't know. It's implied that probably didn't happen. Yeah. Is that rabbit death? You had no idea that worked into this. So is everybody cool what I'm doing? I'm just getting all my dx dy stuff together. Pull this thing to the other side. Okay. Plus, no, it should be minus. Alright, so I got all my dx dy stuff together, moved the other stuff over there together, and now I can take my dx dy out. And over there I'm going to be left with 5x, all that stuff over on that side, divided by what I would get after taking dx dy out. Are you guys cool with this? Take that out, bam, divide by the crap that's left. That's the process. If you've done any of these problems, that's pretty much the last couple steps. Now, I want to show you something neat. I don't know if you guys are going to think it's neat. I don't want to erase my beautiful cylinder of death. This death is this theme today, so. Yeah, I know, so I'm just keeping with that. I never mean to kill anybody. Okay, go with me for a second. Attack this like we normally would. Y is a function of x. Right? Because does it really matter what we say, which one? If we say y is a function of x, then I can solve for x and make it a function of y. Even when I can't solve, then it really doesn't matter who's a function of who, because I can't even get the damn thing by itself. Go with me. Here we go. So attack this like we normally would. Y is a function of x. So when I do this, what do I get? We can bring back in our prime notation if we want to, right? Because now y is a function of x. So how would you take the derivative?
Y times
Y prime secant x plus y secant tangent. All right? You guys with me? Go with me. Equals.
Is that a 5 or a dash?
That's a 5.
Okay. Just making
Yeah.
sure.
I don't want to bring in a third variable. You know? Really awesome.
5.
Tangent y plus 5x secant squared y times y prime. 11. Right? You with me? Now, this one feels a little better because we're using the prime notation we're used to, but it's the same. I could be writing dy dx instead of y prime. It'd be the same exact thing. And normally I don't like using Leibniz unless I have to because it's a little extra crap to write. So I kind of want you guys to get used to that. If you only use it really if you have to, really be careful, be more specific with yourself. What's on the bottom? What am I taking the derivative with respect to? Yeah.
So you're saying you can do it like how we regularly do it and then just plug in the D stuff?
No. What's the fundamental difference between what we did there and what we're doing here?
Back to y.
Yeah, y is a function of x. Over there, x was a function of y. So over there you'd have x primes hanging out because of chain rule. Over here we have y primes hanging out. But math doesn't give a shit. Y and x are just dummy variables. Who cares which one is which?
Right.
Go with me.
Oh.
How do I finish this out?
Do y prime by itself.
Get y prime secant x, subtract that 5x secant squared y prime, and then 5 tangent y minus y secant x tangent y, right? Bring that over there, bring that y prime term over there.
Take out a y prime.
Yep, take out a y prime, and then divide by what would be left. Does anybody notice something? Now, what's y prime mean again? In Leibniz notation?
dy over dx.
Alright. So what should be true about dy dx versus dx dy if the universe is at all kind?
Reciprocal.
Yeah. Do you notice that? Look at that guy. And look at that guy. Now, there's also a little negative sign thing going on, but oh well. You guys cool with that? Isn't it? If I did negatives on top and bottom, it would be 5x secant squared y minus secant x. Isn't that the top over there? This would be y secant x tangent y minus 5 tangent y. Isn't that? Except I'm missing a tangent y. Did I throw it out somewhere?
Yeah, you lost it about the second step. Right there.
Oh, here it is. Thank you. That's a good idea to do that so I actually see that I get the right answer. Cool. Do you guys, does that at all seem nice? So do you realize what's going on here? If they ask for dx dy, you can do the same damn thing you've done and just flip the thing at the end. Isn't that stupid? Awesome. And it's kind of nice. It's exactly what you would hope would happen. And of course it's the way it is. If I want to know how much it costs dollars per ounce, and somebody else is like, no, I want to know ounces per dollar. Well, just take that damn thing and turn it over, right? So this is just a rate.
No.
If I can type five words a minute, that's good, Jeff. No, so if I can type 80 words per minute, that means in 1 minute I can type 80 words, right? These are the same situation. And I can do 1/80th and I can figure out exactly what part of a minute it takes me to write one word. You guys with me? We know we can just flip rates. And they represent the same situation. So it's really nice to see the calculus agrees with us. Yeah, if you need dx dy, you can actually just get dy dx and flip the damn thing over. That's nice. You have to know and be comfortable with doing it that way, though, in general. Because that leads into what if there's other variables in there besides y and x. Is to be completely used to the process and divorce it from y and x and what they do and where they have to be. No, the process doesn't care what variables we use. Okay, cool, maybe. Okay.
So is the dx over dy, is that like saying the rate of change of x over the rate of change of y?
Yeah, the rate, how much x changes given a change in y. Right, so y changes a little bit, how much would x change? So, I mean, has anybody ever realized that our whole idea of slope, and I have students who do this all the time, our whole idea of slope could have been turned all the way around? I mean, our equation could have been this. Right? The equation totally could have been this. Right? This one actually makes more physical sense because the steeper it is, the bigger the slope. That's kind of nice, right? But it doesn't matter. In this case, what would this be? X-intercept, right? So sometimes students will do this and not even realize why it works, but they'll say that must be the x-intercept, but they're not even sure why that works. And of course it works, because y is 0, you get b. So in this case, the m's here would be how related?
The derivative of x.
Don't take it too far. We're talking about algebra, yeah. Right, so if I had y, what did we just do a second ago? Y equals 2x minus 1. X equals 1/2 y plus 1/2, right? The y, who cares about the intercepts? They're just whatever they have to be. Of course, the x-intercept is 1/2, so that's cool that it shows up there. You with me? Maybe a little bit. Okay. So that is exactly what's going on here. The rates, if I've got it the wrong way around, I just turn it.
And you change the signs, or what?
Well, it's just because of the way that this worked out, I chose to go one direction. If I just multiply top and bottom of this by negative,
Right.
it's the same thing.
Right.
Yeah. So it was unfortunate we had a little negative change too, but it's not really. I just top and bottom just change the signs. Cool, maybe.
It makes a lot more sense when you compare it to that.
Okay. But this is the way I would really like to see that problem done. Right? Just to get used to, here's the true process, divorced from thinking y is one thing always and x is one thing always, because it's not true. Okay, and then you had...
What does it mean when it writes dy over dx as like dy over du times du over dx?
Oh, okay, yeah. So that's the...
u is the inside.
Yeah. So you can also say...
So that's like the same
Yeah,
thing.
it's the same thing. So
Okay.
prime here would be, you're actually doing df dg, where they call gu, right?
Right.
And then this is what? dg dx. So it's actually not true that these cancel, but the processes allow it to basically be, that's what happens. It's difficult to explain completely. Somebody ever taken logic class? There's a rule in logic where it looks like things distribute, and they don't really. It's just lucky that it becomes that. So what's the shortcut? Just distribute the damn thing, right? I mean, who cares if that's not really what's going on? That's what it looks like it's going on. Here, it looks like these cancel. And that's df dx, exactly what I would want. Cool, go with that. Who cares that that's not really exactly what's going on, right? But that's the relationship between the prime notation and this Leibniz notation. Okay, maybe. So if I had u of w of t, and I had to take its derivative, I could write it. You do the outside with respect to the inside, and then the inside with respect to its inside. I mean, that's the power of it. It divorces the process from the letters. All right, now the process is always the same. It doesn't care what letters the problem uses. And if I added another function on the outside of that, I would just add another piece, dg, du, dw. So overall, I'm taking the derivative of g with respect to t. You guys semi with me?
So she'd still do like the chain rule, right?
Yeah, that's what that is. That's the chain rules. That says take the derivative of the outside function as if the inside was x. Then it would be the derivative of the inside function as if its inside was just x. And then finally, the very inside dude gets a term, right? It's exactly the chain
You're
rule.
putting x as the denominator, you're saying? As if the inside were x?
So when you take the derivative, for example, if I had this, right? And if I want dy dx, just in keeping with the Leibniz idea, how would I do that?
Sine.
No.
Or Or negative sign, sorry.
No. That's a little more right, but just too early. What's the outside function?
The seventh?
Seventh power. So you take the derivative of a seventh power with respect to cosine, which is basically saying, just look at it like it's a seventh power. Take its derivative. Something to the seventh power is 7 times that thing to the sixth power. So that's like this. Take the derivative of the outside function, treating the inside like it's just hanging out, with respect to it, really. And then the next thing says, now the inside function gets a term. So of course we all know that. Now bring it in.
Negative sign.
I like it. Right? So that's what that notation really means. And when you get up to, I don't know, somewhere between Calc 2 and Calc 3, that becomes very important to write it using Leibniz notation, because you'll have all this big string of stuff going on. You want to keep it straight. Okay, so your other question. Okay, so I got a tangent shark in there. Is find the derivative of this. So arc sine is just inverse sine. Oop, of course I'm inside that. I like it. Arc sine of the square root of sine 17 theta. Yeah, section 3.5. Implicit stuff. Now this one's not really implicit. I'm not sure what they're...
This one's introducing that inverse sine.
Oh yeah, that's right. That's in that section too.
1 over 1 plus x squared or minus x squared?
I sure can't remember. I think it's 1 over square root of 1 minus x squared, and then cosine is negative, I think. Well, I never memorized that. That's why I'm not making you memorize that. So, can somebody help us? So eventually we need, cool. 1 over square root of 1 minus x squared, I like it. So the derivative of inverse sine is 1 over square root of 1 minus x squared. If it was inverse cosine, it's negative, which makes sense. All the cos stuff comes out negative. Same thing happens with the inverses, thank God. But I'm not even making you memorize those, so hey. So when you want to do this derivative, well, let's first write this a little bit different. So what's the inside function?
17 theta.
No, not the very inside function. What's the outside function? Inverse sine. And what's inside of it? Yeah, I love it. Okay, good. So when you first look at it, it doesn't matter how many nesting dolls. You don't know how many nesting dolls. I see one and there's one inside. Okay, I know there's an outside function and I know there's something inside. Is there more in there? I don't know. I don't care until I get there. Right? My first step is purely doing the derivative of this, and then this gets a turn, and then whatever the hell it's got to do is going to come next. I don't have to know ahead of time how many links I've got. Okay, maybe. So what's the derivative of inverse sine of something?
1 over 1 square root of 1 minus
That thing
that thing squared.
squared. I love it, which is kind of nice because that kills my 1/2 on there. So that's the derivative of the outside function times derivative of the inside function. What I keep trying to show you guys is when you apply the rules, you don't have to know ahead of time or do the derivatives all at once or know ahead of time what's going to happen. All you care about is there's an inverse sign with shit in it. So I do the derivative of the inverse sign, and then the shit gets its turn, right? The stuff inside.
And if there was
If
more,
shit offends
if
you.
there was more, if there was another chain link in there, you multiply that out.
And I don't care at first. The point I'm trying to make right now is you don't care at first how far it's going. Now, of course you do, because then you have to make sure you have enough paper. But
Oh, yeah.
to do the work, this so far is good. And now I'm going to worry about this. And now I worry about what this involves. But at first I don't. So I get, what's nice in here?
The 1/2s die.
Yeah, the 1/2 and the 2 goes away. Now, technically it's got to be...
Wait, where'd you get that second 1/2?
Second 1/2.
Yeah, that die. Oh no, the 2. Sorry, but it would be. Oh, because you brought it down.
Because that's the rule for the derivative inverse sign. The derivative inverse sign of something is 1 over 1 minus that thing squared. That's the rule.
Oh.
Whatever that thing on the inside is. What I referred to earlier as the shape. Here, I don't know if this is a big deal, but this should be absolute value. But that's going to really make a big difference. Let's see. Is that cool? Because when you have a square root of something squared, it's the absolute value. All right.
Yeah.
And then what happens here?
1/2 cosine.
Good. It's something to the 1/2 power. Careful. What's the derivative of something to the 1/2 power? 1/2 times that something
To the negative.
to the negative 1/2. Now this guy gets a turn. So you do not do derivatives of outsides and insides at the same time. It's a lot like product rule. Everybody gets a turn, not everybody at once. Right? Alright, so you take the derivative of the function that's on the outside, the 1/2 power. Know what a 1/2 power? 1/2 comes out front of the thing to the negative 1/2 because I had to subtract 1. Now this guy gets his turn finally.
Fine.
What's the derivative of 17 sine 17 theta?
Cosine.
Cosine.
17 theta.
And then we got a little Russian doll in there. Times 17. Alright, and that's one of the easier ones to forget. Because you feel at that point like you've done enough. But you haven't. Okay. So let's see, let's clean this up a little bit. Okay. So we get 1 over, let's see, it's 17 over 2 square root of 1 minus sine 17 theta. What's up?
Choose from the
1/2. Gotcha.
And then we have another square root of sine 17 theta. And then on top we have cosine 17 theta. Good Lord. You see, so that's how I collect things. What's on the bottom, what's on the top, bam. Because when you do chain rule, it's all a bunch of, the links are all products. They're all multiplication, right? Times this, times that, times that. So you can just start moving them around within that. Yay. And then one thing that'll help us out with this absolute value here, I thought this would happen eventually. You can multiply this inside, right? So then it'll be 2 square root of sine 17 theta. Now I don't need the absolute value sign anymore because now it's sine squared inside. Okay. Which, you know, it's obvious that's what it is. No. All right. Now what's more important than right now getting completely there is that you at least understand where the steps come from, right? And I'm desperately trying to get you to look at a problem the correct way, because the easiest thing in calculus is to not understand what it's okay to not do all at once. I mean, it's the same thing with all levels of algebra, I think, and all levels of math, is students think they're supposed to be able to do too much at once. Word problems, I think, is like that. Read it once and get the equation, that's insane. So here, I don't have to know all the derivatives I'm going to have to do until I have to do them. The first derivative I have to worry about is the very outside function. I don't care how many stuff is nested inside there. Outside function is my whole world at first. Times the inside derivative. Now I worry about that guy. I mean, that's the process, and that's what's really important right now is do you understand the process? If you make little mistakes on the way in the process, that's much better than not understanding how the process is supposed to work. So you won't lose anywhere near as many points if you forget the 1/2. If you, this is really easy to leave this poor dude off. Because you bring the 1/2 down and then this is left blank. It's like, no, it's got to go down by 1. That kind of mistake, if you don't make it everywhere, it's not a big deal. Right? You're going to make that somewhere. Okay. Is that good, Dan, or is that...
But I thought that had nothing to do with the dx, yx.
Oh, it's okay. That's what I forgot in 3.5 is where they introduced inverse trig derivatives. So 3.5 is not all about just implicit. It uses implicit to get the inverse trig derivatives. So they're going to give you some problems with inverse trig derivatives. Yeah. Okay. You're at least as bummed out as you were when you turned the quiz in. None of this has helped that out. Anything else from homework or... Yeah.
How about that, the one with the asteroid or whatever, it's 30 on 3.5. It became so ugly, I thought maybe I did something wrong.
All right, so they give you... this equation here. The equation of an asteroid. You gotta love it. In my mind, I can see my little triangle shooting that thing. Some of you guys have no idea what I'm talking about.
No.
Palm. I still remember sitting in front of the TV. Whoa, this is awesome. Palm. Oh, yeah. Anyway. Sorry. They have that coming out in 3D now. It's awesome. And they say at this point, -3 root 3, 1. Yeah.
Yeah.
All right. So the first thing I used to do when I looked at a problem like this is to make sure that point actually works. Sometimes the book makes mistakes. I don't know if anybody did that, so hopefully it works.
You just plug the x and the y in there.
So that would be 3 plus 1 is 4. Yay! All right.
The tangent lines.
So they want to find, yeah, exactly. They want the equation of a tangent line to this curve at that point. So we know exactly what that takes. Right? It almost doesn't matter what they throw at us. The difference with this problem from earlier, of course, is it has implicit differentiation. But the only real difference in general is I'm just going to plug both of these in at once. In the past, when I had an explicit function of x, I just had to plug x in, because all that mattered then was where I was on the x. When I have an implicit function, then it matters what point I'm at. The entire point might have to be plugged in. Okay, so how do I start attacking this to get the slope? So of course I have to take
The derivative.
derivative.
Of both, and you get y prime, and you get y prime by itself.
Say again?
You do the derivatives of both, and you get y prime, and you get y prime by itself.
Exactly, and that's because in this case, I really do want what we consider a line is going to be y's over x's for slope. You with me? The early problem with the dx dy doesn't show up nearly as much because it doesn't really jive with what we consider slope
Because
for a
that's
basic
function of
graph.
x. Because the dx dy is a function of x, right?
Because it's rise over run.
Oh, okay.
Cool. So what's the derivative of this guy?
2/3 minus 2/3 x minus 1.
Okay, good. But nothing else, because x prime is, because it would be dx dx. I like it. Plus, same thing here, except,
dy dx.
yeah, dy dx, I like it. Equals, and for some reason I always have somebody leave that as 4, and man, that really sucks. That makes the whole thing so much harder. So be careful. You do derivative on one side, you better do the derivative of the other side also.
Do you do that just to make it even?
You do that because you have to. You've known that since out. You got to do the same thing both sides. So now,
You get y prime.
I like it. Get y prime by itself. The 2/3 cancel, is that cool? Because they're going to divide everything by 2/3.
Right.
So subtract that over, so I get negative x and negative 1/3, and that's divided by y to the negative 1/3, and I can clean this up now. Is that cool? Subtract that, divide by this, I have y prime by itself. So actually you get y prime equals y over x to the 1/3, it's negative somewhere. Doesn't matter, it could be outside, it's a 1/3 power, who cares?
And then you plug that in?
Is everybody cool with that? You guys semi-cool with that? You might not all end up there, I just like to add them out. And now you just plug your point in. Right? It's not going to come out pretty. This problem where I was curious to see, the few people that have graded this so far went far enough with this, and there was one that made a little mistake, but you're not going to have mx plus b that nice. You're going to have mx plus b, but m is going to be and b is going to be right? But it's still going to be a constant x plus a constant. Constants don't have to be pretty. It can be 5 radical 7 minus, So what's going to happen here? What am I going to put in there for y? 1. And what am I going to put there for x? Yeah, these negatives are going to cancel, so I get that to the 1/3. So that is my
M.
That's your slope.
That's just your M, right? And then you
Yep.
do it.
Is that cool so far? Is that
That's probably double cool. Yeah.
double cool? Okay.
That makes sense.
And now you just have to figure out how to get b for your mx plus b. And it's just, just plug that gross thing in. Do not put a decimal there.
Why, you don't like decimal?
I hate decimal. No, it's not that. Why do I say that? The minute you put any decimal there,
You're round.
you're wrong. Right? So it's much better. Dear God, do not put decimal here. And then start working with it. Because the minute you start working with the decimal, you're even more wrong. Because you're going to make an error with how you estimate it. And then when you do more, when you try to solve for b, it's even more off than it should be. Right? So don't do that ever, basically. Unless it's 0.2, then who cares? This is not going to be 0.2. How do you find b? You can do that, or you can do this. 1 equals 1 over 3 radical 3 to 1/3. That's m. X is negative 3 radical 3 plus b, and now solve that for b. Or you can do the y minus y1 thing if you want to. You'll end up doing the same calculations. What's a whole one of these divided by 1/3 of one of these? 2/3 of one of these. I like it. All right, that's all I'll say about that. That's plenty. You're basically there. Is that cool? Enough? Okay. Now you like my Math 175 class. They I told them that they didn't have no reaction. They had like negative reaction. It was like a black hole reaction. It just sucks reaction out. It was weird. I did not want to play poker with any of them. And you guys are becoming that way. Don't be that way. All right. Well, I think that might be enough. We've got to get into new stuff here. Any other quick questions? As if there's any of those existed in here. Okay. We left off. We finished 3.6. So now we all know what the derivative of natural log of x is, right? What's the derivative of natural log of x? Yeah, 1 over x. And now they're going to throw product rules and chain rules involving ln's, and who cares? The rules don't care what the functions are. You just have to know the basic idea of the derivative of that function, and then you apply the quotient or the chain or the product or whatever rule on top of that. Okay. The nice thing with natural logs is they do have those properties that you can simplify the expression before you attack it with calculus, which is a really nice idea. There's just a couple things I want to talk about in section 3.7. Section 3.7 is basically applications of derivatives. So they go through all these different, they have chemistry stuff in there, business stuff, physics stuff. Sweet. But there's just a couple I want to work on specifically, and then the rest I want you guys to bring questions about. What I want to look at is like number 2 in section 3.7. So look at that. Notice all the parts to it. I'm going to call it S just because in physics S is the position function. And then how do you get to the velocity from there? Yeah, because S prime would also be known as what in Leibniz notation? ds dt. And the prime notation is okay here really because you know that it's in function of t. So when you see the prime, you're taking the derivative with respect to what you're considering to be the input variable, the independent variable, right? It's only when they're all mixed up you have to really be careful about what you mean. That's what. And the other thing about Leibniz notation is it really helps with units. Do the units make sense here? S would be in meters or something. Does this say anything about? No. Is it in feet?
Mm-hmm.
Oh, here we go. Well, I think, yes, thank you, feet. So it's feet per, I think it's in seconds, right? All right. You guys, so that, it makes sense. Change in position would be a certain number of feet. Change in time would be a certain number of seconds. Feet per second is the velocity. Cool. So the calculus symbol actually makes sense unit-wise. How we doing? So Leibniz notation really helps. The primes doesn't show me that. It's less to right, but doesn't show me the units. So, of course, the first part here asks me, find the velocity at time t. So, like you said, that just means take the derivative. What do you get there?
Derivative or t to the third.
Yeah, 0.04 t to the third.
Minus 1.12 t to the third.
I like it. Cool. So that's my velocity. Velocity is the first derivative of position. Cool. That's one of my favorite sounds.
Oh. Wait, where'd you get the... Oh, got it.
All right, there it is again. All right. What is the velocity after 3 seconds? And what they really should say is at 3 seconds, but they mean right after 3 seconds. What's the velocity? So we got the velocity function. So part B is easy, so I'll let it be easy. Velocity at 3 seconds. Just figure out what that is. Put a 3 in there. And whatever the hell that is. 1.08 minus, I think it's 0. Is it 0? Somebody help me out. Yes, it's 0. All right. Of course it is. That's stupid. You always look for tricks like, if you took one of these 3's out here, it's 0.12, 3 squared, 0.12, 3 squared, so of course that's 0. So what we're getting towards is what I said earlier. In this section, the derivatives mean certain things depending on what level of science they're coming from. So in physics, very often it's these kinematic formulas, these formulas of motion, position, velocity, acceleration, right? And other ones you have like flow rate, you have, I don't know, cooling, Newton's law of cooling for physics and stuff. So it all depends on the level of science, how you interpret the derivatives. The math just does the derivatives. You interpret it however the hell you want to. Cool? So, let's see, part C. When is the particle at rest? Well, we sort of know that. We know one piece of it already. The particle is at rest when its velocity is 0. So I know one position already where it's at rest. When's the particle at rest? When it's 3 seconds, that's at least one answer, but that's not all of the answers possibly. All right, what are some more answers here? Looking at the velocity of t, it's 0.04 t cubed minus 0.12 t squared. How do I get all those answers? Equal to 0. So I can divide by 0.04, for example, right? Make this thing look a little nicer. T cubed minus 3t squared. Is that cool?
That's a 3.
That's a 3, yeah. Just divide by 0.04. Just to get that crappy. Remember, I don't like decimals, so I want to kill them.
1/3 or 1 cube. What is that? No, to left. Yeah. Oh, t cube. Oh. Alright, got it.
Alright. And then here I can just factor. So there's our 3, right? There's our 3, and of course the time. Where else? 0, which kind of makes sense. It doesn't have to be, because you can define your time to be whatever. And NASA likes to do the whole t minus 17, which means it's 17 seconds until it's going to last. So that's like negative time for them. Nothing's happening yet, so it's negative time. Everything starts the minute it starts to lift off. So it kind of makes sense in general when we say at t0, the train hasn't left yet. It starts moving, we normally start the clock, but in physics, you can start the clock wherever the hell you want it to. Here it happens to be t equals 0, t equals 3. So at those points, it's stationary. Right, the velocity is 0. It might be starting to move. It might be turning around. Right? Can't turn around unless I go to 0 velocity. Right.
Like you said, turning around at 3?
Yeah, it could be turning around. It could be starting. I don't know. Yeah, they didn't really give me any. Well, later in part H, they say from 0 to 8 for time. So I don't know if that's true for everything. So what about part D? When's the particle moving in the positive direction? And of course, positive direction movement would be denoted by what, do you think? Velocity would be positive. So in physics, positive and negative velocity is fine because the positive and negative are just directions, right? In normal life, if I back my car up, I'm not going to say I'm going negative 20 miles an hour. I was going negative 20 when I hit the wall. I don't know. That wouldn't fly too well. But in physics, we wanted to know the direction. So if I want to know the positive, when is the velocity positive? I just do that.
So,
And to tell you honestly, we have a way we could do that pretty quickly. Yeah.
using the car example, would that be like, to reword it, you'd be going 20 miles per hour in the negative direction? Or not like...
Yeah, in English we would say we're going 20 miles in reverse. So in physics you would see that written on the paper as negative 20 miles per hour.
Okay.
Yeah, so that's what we understand that to mean. Not that we have like some negative length or something, it just is the direction we're going in. Cool. So remember, we already know where all the zeros are. The zeros are at 0 and 3. Let's see if you guys remember. This is where pre-calc really comes in handy. If I'm doing this right now with my pre-calc class, and they love it. If I know these are the zeros, the only possible places it could change sign is at those positions. So if I plug in something, just pretending for a second that negative time works here. If I plug in a negative 1 into the velocity, where's it? Here we go. So I took the point of 4, it doesn't matter, that's positive, who cares? If I put a negative 1, it would be positive times negative is negative. Does that, you guys remember doing that kind of thing? Investigating where something was up and down? Okay, so negative, it's negative back here. If I put a 1 in there, I get positive times negative. Still negative. And why does it make sense about where 0 came from? Let me see how much you guys remember about pre-calc. The root that 0 came from is even power, so it's got multiplicity 2. So it's going to turn. It's not going to change sign there. Holy shit, the whole thing has purpose. I should have invited my pre-calc class here tonight. Maybe they would have. No, I don't think they would. And then when you plug a 4 in, now it should change sign. Positive, positive, yeah. So now it's positive. Because the 4 came from an odd degree term. So it's going to go through that root. Okay. So where is this positive, moving in the positive direction?
Anywhere bigger than 3?
After 3 seconds. I love it. Or t greater than 3. Cool. Because at 3, of course, it's just sitting there. So first it's moving backwards, maybe it's like that. And then it turns at 3 seconds, and then it starts moving forwards in 3 seconds. That was an awesome visual, I know. Now here's the freaky part. Find the total distance traveled. Why is it wrong to just do, and let me see, find the total distance traveled during the first 8 seconds. So I guess they're considering this is where it starts, so this doesn't exist back here. Okay.
What did you say?
They didn't write that problem very well. Now we understand that they're starting at 0. That is the true starting point. Is that cool? So this is not really there.
Oh, right.
We're not considering.
T equals 0. Right.
Yeah. So find the total distance traveled during the first 8 seconds. Why is this wrong?
Because you gotta
That gives you
calculate
loss.
in the negatives, right?
Yeah, it's calculating. It's going to like take your negative and then add on top, and then it's going to cancel out. But that's silly.
It's just,
If I go back 4 feet and then I go forward 4 feet, I haven't gone 0 feet. I've just traveled 8 feet. Now in physics, we have an idea of total displacement. I am back where I started, so I've effectively done nothing. Right? But thankfully, I'm not tired from it. But if I'm a little more tired than I would have been if I didn't go back 4 feet and forward 4 feet. So I know something happened. So what do I have to take into account then?
how far you go to 3.
Good. So 3 seconds is the dividing point. So I just figure out how far did I go at 3 seconds. And then I figure out how far did I go from that to 8 seconds.
And then you subtract them. Or you don't have to subtract them.
You add them together, making sure they're positive.
Oh, okay.
Right. Does that make any sense?
Yeah, because a negative, because you're getting a negative direction to
Yeah,
3.
so what's S of 3?
It's going to be a negative number.
Let's see. What is S of 3? .81 minus 1.8, negative 0.27. No. Yes. I don't know.
I get it. I don't know if I did it wrong.
Oh, yeah, 3's... No, the velocity... Careful now. Here's a really good point. This is the velocity equation. Right now, we want our position equation. Right? So that's what I was talking about earlier. You've got to be careful about which one's F prime, which is F double prime. In this case, they all have different names, which is nice. It'll make it easier to tell what to plug it back into. Right now, I want to know how far did I go, so I want to use the position function. So what do you guys get for that? All right, good. So I did that, right? So I want the absolute value of that for my total distance traveled. What's my position at time 0? I got to be careful. Where am I at 0 seconds? I'm at 0. Cool. So at 0, I'm at 0. I don't need all that. 0 seconds, I'm at 0. So this is position. At 3 seconds, I'm back 0.27. So I've gone this far. And then if I do S8, where am I at 8 seconds? So now I turn. What do I do at 3 seconds?
You
Turn around and go back. So I'm going to be somewhere at 8 seconds. So you're going to have to add this 0.27 on, and then you're going to have to add this whole distance on here. So you guys get this idea. So drawing this little diagram is not a bad idea. What is S8? So man, I don't want to do that in my head. Don't make me. 20.48? So I'm at 20.48, so you just take negative 0.2, you take 0.27, add it to 0.27. That gets me back to 0. Is that cool? 0.27, add it to 0.27, and then you add that to 20.48. That's your total actual distance traveled. Okay, so it'll be 0.54 plus that, so it'll be feet. Oh, you can do it, Jeff. You're just doing 0.02 feet. Okay. Yeah.
So that kind of tells you that it was speeding up when you get to 8.
Yeah, what have we not done that would talk about where it was speeding up, slowing down?
We have
Acceleration. Yeah, we haven't looked at the acceleration.
But if you saw it, it's not going at the same pace, right? Because
Yeah,
if you go
we'd
3,
expect it to slow down here because it's got to go to 0. So the acceleration has to be, if it's really going fast here, I'd have to have big time acceleration, deceleration in that case, right? Negative acceleration.
Yeah, and then you could.
Well, in this
you could
case, it
find
would
that
actually
by
be positive, the other direction. But you would
find that by like.
one of the hardest things for physics students to understand is when I press on the brake in the car, my velocity is still positive, but my acceleration is negative. That's why I slow down. If it was positive, I would just go faster in that direction. That would suck. Do they talk about acceleration here at all? No. Yes. Part G it does. Part F is this kind of diagram. So I'd say draw it before you do part E. And then finally, part G and H. G is find the acceleration. So acceleration, what would it be? The equation. Yeah, second derivative. So here's the first derivative. This is the velocity. So then you just take its derivative again. It'd be 0.12 t squared minus 0.24 t. You guys with me? And some of you guys, I think this came up before. The next derivative would be the jerk. I love this, called the jerk. And if you rode in the first car I ever owned, you would know. Some of you guys know that maybe right now. Is there a car in? Yeah, so the change in your acceleration, if that's big, that's when you get that that kind of thing, right? And mine did that. Oh, poor little thing. Did what it could. So that's the acceleration time t, so the acceleration time 3. I'm not even going to worry about it, you just throw a 3 in there, right? That's pretty easy. When you take derivatives, you get new functions that you can plug stuff into just like you get any function. And then part H just says graph this, and you can use a graphing calculator. Graph the position, velocity, acceleration functions. When is it speeding up? That would be when the acceleration is
Greater than 0.
And when is it slowing down? And actually, it's I don't want to get all. That's fine. Okay, so I think I assigned a couple like one like that, and then there's a few with nowhere near as many parts to it, but they still relate to position and velocity, acceleration. And then I have a couple from different parts of science, like. Oh, let me see. I think number 12. I think I did every third one here, right? Can't remember now. 15, yeah. 15 and 18. They give you the equation. You just have to work with the correct derivatives. So that's why I want you guys just to try this out. It all depends on what kind of snags you hit. So come ready with questions next time. Right now I want to focus on... Damn. Getting a little bit into section 3.9.
Can you really quickly define, so S of t is a function of what?
So S of t is position.
Position.
Now I notice the book uses
What is
F
that?
of t for
What does that
position.
S stand for?
Position, obviously. No, I don't know. I think I looked it up at one point, and I can't remember why they picked S. It's probably, M for slope is a French word. I don't think it's marche. I think it's... Yeah, it's mope, exactly. S is position.
Position.
Yeah. And then if you do S prime, you get V, velocity. And if you do S double prime,
Acceleration.
you get acceleration. S triple prime would be the jerk, but I don't think they talk about that too much.
What do you mean jerk? Like
That movie with Steve Martin? No, I was hoping that the whole thing I did meant something, but... Jerk is when you have a very sudden change in acceleration, is when you feel it. Now, jerk in general, the name unfortunately sounds like it has to be some big change, but I could slowly increase my acceleration. So acceleration means my velocity is getting bigger over time, and if I increase the rate at which I'm increasing my velocity, that would be the third derivative. That would be how my acceleration is changing over time.
Kind of like rolling,
Does that make sense?
kind of like rolling onto the throttle. Going back to your car term.
Yeah.
As you start from the stoplight, you kind of does this. You're
Oh,
slowly-
certainly, exactly. Yeah. So if you held,
Yes.
yeah, I like
Give
it.
it one jerk and here we go.
That's well, yeah. That's the whole jump from 0 to something.
Right.
Okay. All right, so that's enough of that. Let's get into, I just want to do a little bit out of 3.9. Maybe a little less than I was going to. 3.8, yeah, totally. It's not in our syllabus. It's not in our curriculum. There's no homework assigned from it.
You don't like exponential growth, do you?
Huh?
You don't like
Oh, I hate it. It's terrible. Almost as bad as really? It's the same thing?
Yeah.
Actually, this one's just totally, they just didn't want to do it in general. Oh, there's Newton's law of cooling. Well, that'll be all right. Okay. So this is the true word problem section for calculus. And it's nowhere near as bad as word problems in algebra. Because in algebra, your word problems, you have to create your own function based off the situation. Remember that? That's why word problems are so hard at first for people. This one, they kind of give us the functions to work with. We just have to be careful about the information they give us. What symbols would we use? Where would they go in the function? So let me see what, if you figure out what I'm talking. My example with my monkey woman is from the movie Displacement. There's this big cylinder basically running down this lab that had part of it underwater. So unfortunately there was
And there was a shark in the water.
several sharks, big ugly sharks.
There's a shark.
That's
in
when the
water,
black guy
that's
died,
the movie,
right?
dude.
Yeah. So let's no, he's fine. I like that. That part they kept throwing out like who's going to die? Who's going to Anyway. And then anyway. So down here there are these doors that are open. So there's water flowing in from the ocean. So all around here is the ocean. There's water kind of flowing out into these hallways. So there's a flow in and a flow out. So it's not going up as fast as it could be if those doors had been closed. Are you guys kind of with me?
Yeah.
Of course, the sharks just wanted to sink the whole thing so they can get at the humans and eat them because they're hungry. And actually escape. So there's a couple doors that have this flow out into these hallways. So let's say if the flow in was, what you got, Jeff? Was like, say 9,000 cubic feet per minute. And let's say the total flow out was 8,000 cubic feet per minute. What overall, what direction would this water be going? Because overall, how much
1,000 cubic
in,
feet per minute.
right? So there's a complete flow of 1,000 cubic feet of water per minute coming in. Now, can you take a second just on that? What symbol would you use to denote that? It's not just one letter. What entire symbol would you use to denote that?
Delta or plus or?
Think back to what I was saying earlier about what relates to units really well. So what's cubic feet? Volume, I love it. And this is all about, is my volume static? No, it's changing. So every minute I'm getting 1,000 more cubic feet. So that's change in volume.
dV over dt.
I love it. So dV over dt. So that's what I'm talking about. The big key with these word problems in calculus, with the related rates, is the information they give you, can you figure out what symbol goes with it? Because then when you do your derivatives of the volume function for this, you know where the hell to put it. Okay, so that's one thing. Okay. Now, what is the volume formula for this? And it's not for the whole cylinder, by the way. is the volume of water that's currently in there. Because that's really what that relates to, right? That's how much this is changing. So there's so much water in there right now. So let's say, this is going to come in later. Let's say she's at the 200-foot mark, and this is at the 120-foot mark. That's going to come in later. Don't worry about it yet. I don't know how much time does she have to get herself up over that freaking ladder before she gets in. Right, so chemical is saving the lives. So what is the volume of this water? What does it relate to? What do I need to kind of know here? Well, let's do this. Let's just get a feel for this. What's the volume formula for a cylinder? Who remembers? What's the base? Base is a circle. What's the area of the circle? Pi r squared times the height, 11. So volume is pi r squared h. I don't know why I left so much. Okay. So that's the function I'm working with. Now what's constant there? In terms of my volume of water. I like pi is constant, that's right, but which variable is actually constant here? Radius, right? And the radius is 10. I love it. So my volume formula really for this water depends on how high it is. The volume would be pi times 10 squared, so 100 pi h. That's my volume formula.
Would you create a formula for h because it's always rising per minute?
We're going to. I love it. But we're going to use what to get there. What you just said, what's the symbol for what you just said?
dv of dt.
D what dt? You weren't talking about volume, we were just talking about
Height.
height, so dh dt. So really what I want to know, in order to figure out how long she has to live, I have to know how quickly is this coming at her. Because the quicker that is, the quicker the shark can get up to her. You guys with me?
Yeah.
Please like this problem. I made it right before class. And I thought this is kind of cool. If they know anything about this movie, it'd be even better. So I've identified this piece of information. I gave it its correct symbol. I have the volume formula that works for this situation, right?
So you're going to put 1,000. You're going to set it equal to each other.
Now here's where what we talked about earlier comes in. What am I taking the derivative with respect to?
To the time.
Time. And both velocity and height are functions
Of time.
of time.
So you just cancel them out.
So this is a little different than before. This is a third variable. Wait, there's a third variable that's behind the scenes, but the idea is the same. It's just that now both of these variables in my equation have to have their own dt, right? Not just y prime or x prime, but it's actually going to be both of them, because everything depends on time in this equation. So when I take its derivative, this actually, I started with a very nice problem here. There's not a lot going on. Derivative of v with respect to t is obviously just dv dt. And this side is almost too easy. dh dt. It's a nice one to start off with, just so you can see multiple d something dt's running around in here, right? That's the slightly new thing for this section. But hopefully it just makes sense based off what we did earlier. We're not taking a derivative of a variable with respect to one that's in the equation already. We're doing a third thing that's behind the scenes. They both are being governed by t. And if you did any parametric stuff before, which a lot of you guys claim not to, that'll make even more sense. So now, what in here do I know? Yeah, no, dv dt is 1,000 cubic feet. All the units equals 100 pi dh dt. So now I can solve for dh dt. What would dh dt be?
1,000 divided by 100 pi.
Yeah, so 1,000 by 100 is 10 divided by pi. What are the units on it?
3.14.
No, what are the units? No, come on, it's height. Right, feet per second, dh, feet, dt, seconds. Is that cool? Heights in feet, times in seconds. Or minutes, I'm sorry. Is it minutes? Yeah, minutes. My bad. So the height changes by 10 feet every pi minutes. Of course, we all measure time in pi. but we'll stick with that. So how long does she have before the water is up to her? Yeah, it's got to go 80. You have your good old distance equals rate times time. Right? So you have 80 divided by the rate is 10 over pi. Gives you how much time she has to live. Yeah, good. Because you multiply by pi over 10, so you get 8 pi minutes. So about 25 minutes, 20 something or other minutes.
The 80s from the distance from the water to the ladder.
Exactly. So that you didn't have to worry about to the very end.
Okay.
You guys semi with me?
Yeah, I was with you on the last part. The 10 pi, why don't you just figure out 3.18 once you just divide that into it? And then just
You could. You'll still end up with whatever that is.
Okay.
You'll just be a little more off.
Okay.
So the longer you keep away from doing decimals, the more correct your final answer is.
Okay.
Now you can make this into a decimal if you want to. I'm not going to tell her. You got 8 pi minutes to live. That might occupy her until the sharks get up to her, but no. 8 pi is there. All right. You guys get a feel. The most important part of this whole thing, there's 2 important parts. Making sure that you identify the information they give it the correct symbol. Because the next important part is taking the derivative of this implicitly, but every variable now is going to be dependent on this third variable. Most of the time it's going to be time, but it could be something else. All right, and that's plenty. We'll get deep into section 3.9 next time.